Welcome back to an introduction to oceanography from the textbook Essentials of Oceanography, written by Tom Garrison and Robert Ellis. This is the 8th edition from Cengage Learning. I'm Dave Cocchiarella, and today we are talking about water and ocean structure. So we're going to get into the unique properties of H2O, of water, and then we're going to talk about the structure of the ocean. Not only what does it look like, but what does it feel like? What is the temperature, and how does it change? And how does the salinity change, and the density of the ocean, and how we know about what's on the bottom of the ocean. That's all part of the lecture today, water and ocean structure. So let's get to the main points.
First, heat and temperature are not the same thing. Temperature is an object's response to an input or a removal of heat, and not all substances respond in the same way. We also will talk about the fact that water resists rising in temperature as heat is added. It means it slowly heats up and it slowly cools off. It also gives off heat when it freezes and absorbs heat when it thaws. That's latent heat, and that's going to be a very interesting aspect of water. These properties of liquid water help to moderate the Earth's temperature, and so we're also going to look at how the water molecule is structured to make it a very, very powerful solvent. We're also going to talk about how the ocean is density stratified, dense, cold, and salty water underneath less dense, warm, and fresher water. We're going to take a look at light and how it moves through water, and how sound and light move in different ways through water. And then we're going to talk about how the ocean is a vast reservoir that affects the Earth's climate. It can be a vast carbon reservoir. So you very likely have seen this view of the hydrologic cycle many, many times, water circulating constantly between the oceans, the atmosphere, and the reservoirs of fresh water. The whole numbers represent thousands of cubic kilometers of water transferred each year, and the percentages show the proportion of total global water in different parts of the cycle. All right, let's talk a little bit about solutions and mixtures. So what are solutions and mixtures? A solution is like taking fresh distilled water, absolutely pure water, and putting a tablespoon of salt in it and mixing it up. The salt dissolves into the water. It becomes part of the solution. Then you have salt water. So a solution is made up of two components with uniform molecular properties throughout, such as salt water or sweet tea. The solvent, which is usually a liquid, is more abundant, and the solute, often a solid or a gas, in the case of salt water, salt, or in the case of tea, it would be the tannic acid. They're often a solid or a gas, and they are the less abundant component. Now, solutions are different from mixtures, all right? In a mixture, the components retain their separate identities, so it's not uniform. Think of soup, like vegetable soup. It's a mixture of different things that all retain their separate identities. A compound is a substance that contains two or more different elements in a very fixed proportion, like H2O. We have two hydrogen atoms, one oxygen atom, very specific proportions, two different elements making up a compound. An element then is a substance composed of identical particles, all the same atoms. So oxygen is all oxygen atoms, and those atoms cannot be chemically broken down into smaller substances. A molecule is a group of atoms held together by chemical bonds, either ionic or covalent, and atoms are the particles that make up elements. So a water molecule is composed of two hydrogen atoms and one oxygen atom held together by a covalent bond. It makes it a polar molecule, having a positive and a negative side. A molecule is a group of atoms held together by chemical bonds. So those chemical bonds, the energy relationships between atoms that hold them together, are formed when electrons, the tiny negatively charged particles found toward the outside of an atom, are shared between atoms or moved from one atom to the other. Now, when the electrons are shared, as they are in the water molecule, it's a very strong covalent bond. When the atoms move from one to another, it's a question of like opposites attracting, and negative and positive atoms attract, making an ionic bond. An ionic bond is not nearly as strong. So in the case of your hydrogen atom, which is right here, this is going to be your hydrogen atom, we have the nucleus and one electron. Now, electrons move around nucleuses, the nuclei, in shells, and the first shell can contain two electrons, and hydrogen only contains one. The second shell, as we see here, with the oxygen atom can contain up to 6 electrons, and each subsequent cell can contain, sorry, that's not correct, up to 8 electrons, and each subsequent shell can contain 8 electrons. When 2 hydrogen atoms come toward 1 oxygen atom, they share this electron. This electron gets into this shell, that electron gets into that shell, and then what you have is the 1 proton of each hydrogen atom, the 1 proton of the oxygen, the 2 inner electrons in the 2 inner shell of the oxygen, and then 1, 2, 3, 4, 5, 6, 7, 8 electrons in that second shell. The oxygen atom and the hydrogen atom are sharing this electron. They're sharing that electron. And because of the positive nature of hydrogen, the negative nature of oxygen, the opposites attract, and you get this very specific 105-degree symmetry between the hydrogen atoms, creating this molecule that is a polar molecule, meaning negative on one side and positive on the other side, and looks a lot like Mickey Mouse. All right. What holds water molecules to each other? Hydrogen bonds form when the positive end of one water molecule bonds to the negative end of another water molecule. So the positive hydrogen end connects and bonds to the, it is attracted to, makes an ionic bond with the negative end of the oxygen. So that is the hydrogen bond, and it is a very, very strong bond. So what are the 2 most important properties of a water molecule? Well, it's cohesion and adhesion, and it's because of this hydrogen bond. The hydrogen bond allows cohesion, the ability of water molecules to stick to each other. That creates surface tension. Take a drop of water, put it on the table. It doesn't spread out to one thin layer of one molecule thick water on the table. It stays in a little, a little drop. That's the surface tension holding that water together. The same as if you have a drop of water hanging from the tip of your finger that you've got hanging upside down. That water molecule hangs there because of surface tension. Well, adhesion is the other important property of water. It's the tendency of water molecules to stick to other substances, and because of those adhesive properties and the polar nature of the molecule, it makes it an excellent solvent. So what is the difference between heat and temperature? We talked about that at the very beginning of the lecture. Heat is energy produced by the random vibrations of atoms or molecules. All atoms or molecules move. Even in a solid, they may be rotating or vibrating. In a gas, they're zipping around in the air, in the atmosphere, or whatever is containing the gas. And in a liquid, they move by each other, squishy and all liquidy, all right? So all molecules and atoms move. They may be zipping around, they may be vibrating, or they may be rotating. The hotter the molecule or the atom is, the more they vibrate and move. And the colder the molecule, the less they vibrate and move. The temperature is an object's response to the input or removal of heat, meaning when you input heat into a substance, those molecules begin to move more quickly, and that change in movement is the temperature. So the temperature is a measure of the average speed of molecules. Now, heat is all of the motion of the molecules in a substance, and temperature is the measure of the average speed of those molecules. Heat capacity is a measure of the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, and that heat capacity comes in the form of a calorie. It takes 1 calorie of heat to raise 1 gram of pure water by 1 degree Celsius, and we see that on the chart of heat capacities of common substances. Pure liquid water requires 1 calorie per gram. Water has a very high heat capacity. It takes a great deal of heat input to change the temperature of water. It also requires a great deal of heat removal to lower the temperature of water. So the relationship here between density and the temperature of pure water. So over here at A, we're at about 19-20 degrees, 20 degrees Celsius. Here we're at 10. Here at B, we're at 3.98, a very specific temperature Celsius. That is the maximum density of water, 1 gram per centimeter, cubic centimeter, that is, 1 little cube of water, 1 little centimeter wide cube of water. And then the density of water drops rapidly as it chills, and then drops significantly as it goes from liquid water here at C to solid water at D. So here you have very warm water with a very low density, and as it gets colder and colder and colder, the density increases. So that makes sense, right? Density is the volume, the amount of a substance divided by its volume. So the density of a square of styrofoam is significantly less than the same size square of lead. There's way more molecules stuffed in that same size square of lead. It has a higher density. So it's mass divided by volume. And as the mass increases in the same volume, then you get higher and higher density. As the mass decreases in the same volume, you get lower and lower density. So what do all substances do when they get cold? They contract. So the contraction of water causes it to become more dense, right to 3.98 degrees Celsius. That is the maximum density of water, pure water, 1 gram per centimeter. Then as it continues to chill toward freezing, the molecules of water begin to arrange themselves more in a lattice formation, the hexagon that we think of as a snowflake, and they take up more room, and so the volume increases and the density goes down. This is still liquid water at 0.999 grams per centimeter. Once it freezes, the density of water goes down to 0.917. So you can see the density of frozen water is significantly less than the density of warm water or even cold water. And that's why ice floats. When the water freezes, the density of that same amount of water is much less and the ice floats. So the lattice structure of an ice crystal showing the hexagonal arrangement, that's the hexagon, we think of the 6 sides of a snowflake, that's your hexagon. During the transition from liquid to the solid state, the bond angle between oxygen and hydrogen atoms in the water widens from 105 to 109 degrees because of the change in temperature. This change allows the hydrogen bonds in ice to form a crystal 3D lattice. That's how you get that hexagon in a 3D lattice. Now, at this point, these are all individual water molecules. The space taken up by 24 water molecules in solid lattice could be occupied by 27 or significantly denser amount of water molecules in a liquid state. So solid water is less dense. It's 9% less dense. And because of that, again, ice always floats. All right, so let's talk about those states of matter. I referred to the phase at one point. A phase or a state of matter, there are 3 states of matter. You have a gas, a liquid, and a solid. Now, some say that plasma is a 4th state of matter, and that's very true. But in this case of physical science, we're going to talk about these 3 states of matter, gas, liquid, and a solid. So a gas is a substance that can expand to fill any empty container. Now, atoms or molecules of a gas are in high-speed motion as they move in random directions. They move just about any different way. A liquid is a substance that flows freely in response to unbalanced forces. So if you've got a glass of water, it's sitting there perfectly still. If you tip the water over, now you have an unbalanced force, and that water will flow freely because of that unbalanced force. But it does have a free upper surface in the container if it doesn't fill that container. So gas fills any container that you put. If you only have 2 water molecules, water vapor in a container, it'll fill up that entire container. Water will not fill the entire container. It will have its own upper boundary, and that's one of the big differences between gas and a liquid. All right. Atoms or molecules in a liquid move freely past one another as individuals or small groups. Liquids compress only slightly under pressure. Gases and liquids are both classified as fluids because they both flow easily. A solid is a substance that resists change of shape or volume. A solid can typically withstand stresses, like you can press on the table and it won't just move or bend. A solid usually breaks suddenly. On Earth, water can occur in all 3 states, which is one of the things that makes Earth very, very unique. And here is the change in state going from a solid piece of ice at 40 degrees below Celsius to ice at 0 degrees Celsius to ice transitioning from ice to water and then heating up from 0 degrees Celsius to 100 degrees Celsius, the boiling point of water, and then vaporizing into the air. And what we see here, these flat areas, this is where we have additional heat as input. Okay, so we've warmed this very, very cold ice up from 40 below to 0 degrees Celsius, and we've only put a little bit of heat into it. This is the heat at the bottom, heat and calories. Now we get to this frozen ice, and it takes a tremendous amount of heat with no change in temperature to melt it. Then we add heat again, just a little bit at a time, and water warms up. It warms up to 100 degrees Celsius, but then it takes a tremendous amount of heat input to get that water to turn into gas. And the reason why that is because in order to get this ice to turn into a liquid, you've got to break down the bonds between the molecules. They're very, very well structured, very, very tight, very well bound in a solid. So you have to put a tremendous amount of energy into that solid to break those bonds and turn that solid into a liquid. Now you have a liquid up at 100 degrees Celsius, and to get that liquid to turn to a gas, again, you have to put a tremendous amount of heat energy into that liquid to break the bonds. The water molecules are literally bound together, but tremendous amount of heat input, and those water molecules will break apart and become water vapor. And so lots and lots of energy is required to turn liquid water into vapor. Interestingly enough, when water vapor then condenses, goes from vapor to a liquid, it's going to release all that energy. And then when water goes from a liquid to a solid, it's also going to release energy, significantly less, but it will release energy. So what we learn from that is that it takes energy in to go from an ice to a liquid. By removing energy out of the environment to cause that ice to go to a liquid, you literally chill the environment. The same thing happens when you go from a liquid to a gas. When evaporation occurs, it takes energy to go into the liquid for it to evaporate, thereby chilling the environment. But the opposite occurs when you go from a vapor to a liquid, condensation. You release heat, and therefore condensation is a warming process. And when you go from a liquid to an ice, you also release heat. And again, on a global scale, that change right there, that warming when you turn to ice and cooling when you melt, actually helps to moderate the world's temperature. It keeps it from being too extreme, one way or the other. All right, so the energy input or output associated with water in the three states of matter. We have to add 80 calories of heat to change a gram of ice to a liquid. To get a gram of ice to turn to a liquid, we have to add 80 calories of heat. Where does that heat come from? It comes from the environment. It has to take it out of the environment. So if you have ice in water and causing the ice to melt, it literally chills the water. Or let's look at it a different way. You have ice in your tea or ice in your soda. Your soda's warm, your tea's warm. You put ice in it. The melting of the ice requires 80 calories of heat. Where does it get the heat from? It gets it from the soda or from the tea, thereby chilling the tea. Another way to look at this is going to the beach with a case of warm soda or beer, whatever it is. You throw it in your cooler. If you just throw it in the cooler, you've got to wait. But if you put water in that ice and cause that ice to melt, it will chill those cans of soda or beer much more quickly, because the heat energy required to break down the bonds of the ice will be pulled out of that warm soda or beer. Same thing happens when you go from a liquid to a vapor. And this is basically just evaporation. Liquid to a vapor, it takes 540 calories to break the bonds of the liquid to turn it into a vapor. And so evaporation is a cooling process. Here's a really great example. Take water, put it on your arm, let it evaporate. It'll feel cool. When you sweat, the point of sweating is not for the liquid sweat to make you feel cooler, but for the sweat to evaporate off your body and requiring 540 calories per gram of water on your body. And it pulls that heat energy, those calories, out of the atmosphere around you, cooling the air around you. Evaporation, or the evaporation of sweat, is a cooling process. So condensation is a heating process. Evaporation is a cooling process. Condensation is a heating process, and evaporation is a cooling process. Ice to water cools the environment around it. Ice cools the water or the tea that it's sitting in. Water to a vapor, evaporation, cools the air around it. It requires heat to break those bonds, and the opposite occurs. When we go from a vapor to a liquid, we release heat. When we go from a liquid to an ice, we also will release heat. Latent heat is a very interesting thing. It is the latent heat of evaporation, or the latent heat of condensation. It's the heat that's required to break the bonds, is hidden within the water molecule, and when the water molecule goes to a liquid or to an ice, it releases that heat. So it's the latent heat of evaporation, latent heat of condensation. Latent, again, meaning invisible or hidden. All right, so some interesting properties of water. This is in your book. You can read through it. Its ability to dissolve. Water is known as the universal solvent. Its density, its surface tension, its ability to conduct heat, its heat capacity. You can read about all that in the book. Lots more properties of water. Latent heat of fusion, latent heat of vaporization. That's the latent heat of freezing or the latent heat of melting, the latent heat of vaporizing or the latent heat of condensation. And again, vaporization and condensation, the highest heat required of all substances. So the condensation of water vapor into clouds releases tremendous amounts of heat in the atmosphere. So think about water at the equator evaporating into the atmosphere over the equator, then getting moved north as water vapor and condensing into clouds over northern England. It releases tremendous amounts of heat over northern England. This latent heat of vaporization and condensation is one of the ways we move heat north and south from the equator. All right. And because of those unique properties of water, water moderates temperatures, meaning it takes a great deal of heat to warm it up. It takes a great deal of heat removal to cool it off. And what that tells us is that if you're near a very, very large body of water, then your temperatures are going to be much more moderate than they will be if you're far away. So let's take, this is an example between San Francisco and Norfolk, but a much better example, just consider Seattle here and then North Dakota here. Seattle may not get all that cold in the winter, but it also may not get all that warm in the summer. That's because it's very close to the Pacific Ocean, where we know that North Dakota gets extremely cold in the winter and quite a bit warmer in the summer because it's far away from any of the moderating impacts of water. So water moderates temperatures. The thermostatic properties of water are those properties that act to moderate its change in temperature, heat capacity, latent heat of fusion, and air and ocean currents. They all cause large bodies of water to moderate temperatures and moderate climate. And we talked about how the melting or the freezing of ice either releases heat or requires heat. So it takes a great deal of heat to melt the ice. And so when the ice is melting around the Arctic, in the summertime, it takes heat out of the environment, so it actually cools the environment, keeps the environment from warming up too quickly and more ice melting. And the opposite happens. When it gets very, very cold in the wintertime and ice begins to form, that formation of ice releases heat. And again, that serves to moderate temperatures on a global scale. And we can see how currents do the same thing. Ocean currents and atmospheric currents move heat from the tropics to the polar latitudes. Ocean currents move warm tropical water north, like the Gulf Stream. Here's the Gulf Stream. It comes out of the Caribbean, goes up into the Gulf of Mexico, circles around, and then goes out of the Florida Straits and up the eastern seaboard, then moves across toward Western Europe. That Gulf Stream bringing that warm water over to Western Europe is the reason why the UK, while not warm, is certainly warmer than at the same latitude over here in Canada. So atmospheric circulations move even more heat to higher latitudes by the mass movement of water vapor. You evaporate all this water down by the equator, then you move it north, and when condensation occurs, it releases that heat. As condensation of water vapor into clouds occur at higher latitudes, tremendous amounts of latent heat are released through the warming process of condensation. Water is also a powerful solvent. Due to the polar nature of water, it makes it a great solvent. It will eventually dissolve literally anything. You put anything in water long enough, it's going to dissolve it. When we think of table salt, that's actually sodium chloride. So you put sodium NaCl into water, the positively charged hydrogen end of the polar water molecule is attracted to the negatively charged chlorine ion, and the negatively charged oxygen is attracted to the positively charged sodium. And so it literally pulls the chlorine and the sodium apart. So water is a polar molecule and then pulls other polar molecules apart. Well, oil is not a polar molecule. Oil that does not have that polar nature, and that's why water can't dissolve oil. The two will sort of separate. When water comes into contact with compounds whose elements are held together by the attraction of opposite electrical charges, like most salts, the polar water molecule will separate that compound's elements from one another. Water dissolves the compound. The compound's elements can move easily through water by diffusion, the random movement of materials through a solution, which means if you take water, very still water, and drop a tablespoon of salt into the bottom of the water of the glass, diffusion will cause that higher concentration of salt at the bottom of the glass to eventually randomly move throughout the entire glass of water. Eventually, the entire glass of water becomes salty. That's diffusion. When no more of a compound will dissolve, water is said to have reached saturation. The rate at which molecules of the solute are being dissolved now equals the rate at which they're reforming into crystals. So essentially, if you put a whole bunch of salt into water and you start to stir it up, the salt crystals will dissolve and dissolve and dissolve. There'll become a point when no more of that water can hold salt crystals, and then any more dissolution or dissolving of salts will require that some salts recrystallize. And so it's sort of a recycling process where some of the crystals are dissolving and some of the crystals are reforming. The reforming of a solute in a solution into a crystal, that process I just mentioned, is known as precipitation. And that happens in the air as well. You have air, look at the air in front of you. It has water vapor in it. It's just not completely saturated. If you were to saturate that air in front of you, well, then condensation would occur. When condensation occurs, the water vapor molecules in the solution of air are reforming into water molecules, and that's known as precipitation. So NaCl, sodium chloride, does not exist as a salt in seawater. So you don't have like salt in seawater. What you have is its component elements that are separated by the water molecules, and it still tastes like salt because both those elements are there, but they're actually broken apart into the solution. Now, if you evaporate the water, that NaCl will then recrystallize, and what will be left over is the salt. Salinity is the total quantity of dissolved inorganic solids in the water. So salinity, or how much salt in the ocean water, is not just how much salt, what we think of table salt, sodium chloride, but the total quantity of dissolved inorganic solids in water. The average salinity is about 3.5%. Most of the dissolved solids are salts that have been separated into ions, basically the weathering of rocks on the continents. Weathering, whether it's chemical weathering or physical weathering, breaks down rocks into much, much smaller pieces, eventually getting them down to just their ions. Those ions flow downstream and end up in the ocean. That's how we've saltified, essentially, the ocean. So sodium and chloride are the most abundant ions in seawater, but you can see there's lots of others. There's obviously oxygen and hydrogen, but there's sodium and sulfate and manganese and calcium, potassium, and bicarbonate, which creates carbonic acid, which makes the ocean slightly acidic. But any of those major constituents can recrystallize. So magnesium can literally recrystallize in the ocean as magnesium. And calcium can too, calcium carbonate. That's where you get the shells of animals. That's what animals, mollusks and different sea life, planktons, phytoplanktons, and even zooplanktons, they'll take the carbon dioxide and the calcium out of water and then make a calcium carbonate shell. And corals do the same thing. All right. The salinity of seawater. So nearly every element present in the crust and the atmosphere is also present in the ocean. So all the elements that are in the crust of the earth and all the elements that are in the atmosphere eventually break down and get mixed into the ocean, creating those salts at 3.44 grams, that almost 3.5%. If you take that 3.44 grams and break that down, mostly it's chloride, then a lot of sodium, then your sulfates, magnesiums, bicarbonate, calciums, potassiums, and others. All right, and this is the process by which the ocean became salty. This process that regulates the major constituents of seawater. Ions are added to seawater by rivers running off crustal rocks, plus excess volatiles from volcanic activity. Groundwater, that's how you get some of those ions. Hydrothermal vents gives you some of the ions in cold springs. And the decay of once living organisms gives you ions. Ions are removed from the ocean by chemical entrapment as water percolates through the mid-ocean ridge, meaning as the water goes back down into the rocks of the ocean crust, some of those ions are pulled out and lost to the crust. And also different places like seamounts, underwater volcanoes. Sea spray will take some of those ions out. You get uptake by living organisms. I talked about how living organisms will pull carbon dioxide and calcium out to make their shells. Incorporation into sediment. Some of those things are held in the sediment, and eventually the sediment is buried. And then ultimately with sediment, that sediment then just gets subducted back down into the crust. So that's how those major constituents are basically held in a uniform proportions, that cycle. So the principle of constant proportions say the salinity of various samples of seawater may vary, but the ratio of the major salts is constant. So you may have slightly more saline or slightly less saline seawater, but the ratio of those salts is always constant. The salinity is the total amount of dissolved materials in 1 kilogram of water, measured with this salinometer. The ocean is always in a chemical equilibrium. The proportion and the amounts of dissolved solids remains constant. That's the principle of constant proportions. Ions are being added to and removed from the ocean at the same rate. The proportion and the amounts of dissolved solids remains constant and is known as a steady state ocean. So landlocked seas aren't like this. Landlocked seas will just continually have more ions pumped into them from rivers flowing off those seas, like the Dead Sea or the Great Salt Lake, and they just become saltier and saltier and saltier and denser and denser and denser. Processes that add salt, such as weathering of rocks, are balanced with the process that removes salts, such as the burial of sediment. Residence time is the average length of time an element spends in the ocean. All right, there are conservative constituents and non-conservative constituents. The conservative constituents of seawater are those constituents that occur in constant proportions. Conservative elements have long residence times and are most abundant. Non-conservative constituents have short residence times and are usually associated with seasonal or biological or short geologic cycles. So you might have a big algae bloom, and a big algae bloom is going to suck up all the oxygen out of the water, so you, or cause other things to happen. So sometimes biological events or seasonal events or short geologic cycles, like a lot of volcanism, may change those non-conservative constituents. So how about gases in seawater? Most gases in the air dissolve readily into seawater at the ocean surface. So the ocean in contact with the atmosphere, you get lots of great dissolution or dissolving of those gases in seawater. Plants and animals living in the ocean need those dissolved gases to survive. Nitrogen, oxygen, and carbon dioxide are all found in seawater. The proportion of dissolved gases in the ocean is different from the proportion in the atmosphere. Significantly different amounts of carbon dioxide in the ocean than in the atmosphere. Significantly different amounts of oxygen as well. And those differences are largely due to the ability of gas to dissolve in water and in air. And unlike solids, gases dissolve more readily in cold water. If you take a solid, salt, sugar, and you put it in warm water, it's going to dissolve very quickly. If you ever taken a big teaspoon of sugar and put it in cold iced tea, it's very difficult to get it to dissolve. But it's the opposite in water. Gases dissolve very, very easily in cold water. Because ions in seawater react with each other and with water in complex ways, they modify the physical properties of pure water. These are called the colligative properties. The heat capacity of water decreases, its ability to hold heat decreases with increasing salinity. Less heat is required to raise the temperature of seawater than fresh water. As salinity increases, freezing points decrease. Sea ice forms at lower temperatures than fresh water, so it takes colder air, colder water to form sea ice than it does freshwater ice. As salinity increases, evaporation slows. Dissolved salts tend to attract water molecules, so it's very difficult for evaporation to happen in very salty water. And the osmotic pressure increases as salinity increases. This is the reference to osmosis. The pressure on a biological membrane increases as the salinity of the environment increases. Nature tries to achieve equilibrium. So if you've got some biological membrane separating two reservoirs of let's just say water, one is more saline than the other, the pressure pushes that salinity across that membrane and tries to get equilibrium between the two salinities. So gases dissolve readily in seawater. Nitrogen, which is a conservative component, meaning it's always in the same proportion, makes up about 48% of the dissolved gases in seawater. The upper layers are saturated with it. All life needs it, but interestingly enough, most organisms, including human beings, can't actually use dissolved nitrogen. It has to be fixed into nitrates that we can use by other organisms, specifically bacteria, certain types of bacteria. Oxygen makes up 36% now of the gases. Of course, vital for animals. It comes from photosynthesis and dissolved from the atmosphere. It's a non-conservative component. It can change depending on biological activity. There's 100 times more in the ocean, oxygen that is, than in the atmosphere. And there's 60 times more carbon dioxide in the ocean than in the atmosphere. The ocean is considered the great carbon sink, where carbon dioxide can be sequestered and held and kept out of the atmosphere. Of course, carbon dioxide is used in photosynthesis for plants, and it comes also from respiration, or we take in oxygen and then we breathe out carbon dioxide. So do other animals in the ocean. It's also dissolved from the atmosphere, and it's also a non-conservative component. It can change depending on what's happening in the ocean at the time. All right, the carbon cycle, which is actually fascinating, and this illustration does a tremendous job of breaking it down, but it's very, very complex. And the carbon cycle and how carbon sort of migrates through the cycle can have a huge impact on global climate, and part of the reason why over very vast geologic spans of time, global climate has changed. So the carbon dioxide combines readily with seawater to form carbonic acid. Carbonic acid can then lose a hydrogen ion to become a bicarbonate ion, or two hydrogen ions to become a carbonate ion. Some bicarbonate ions break down to form carbonate ions, which combine with calcium ions in seawater. So carbonate ions we either get from two hydrogen ions becoming a carbonate ion, or bicarbonate breaking down. And when you have these carbonate ions, they combine with calcium to form calcium carbonate. And calcium carbonate is hard. It's like limestone, or it's like the shells of sea creatures, or the hard skeletons of sea creatures, or like coral. So when those creatures die, those structures may fall to the seabed as carbonate sediments, eventually to redissolve and then turn into carbon dioxide in the water again. Or sometimes they're buried and compacted and lithified and turned into carbonate rock, like limestone, like I said. But that is the carbon cycle. And as the double arrow indicates, all of these reactions can go in either direction. So carbon cycles through the atmosphere into the ocean, and then into calcium carbonate, which can dissolve or be buried, and then sometimes buried and lithified, turned into rock, sometimes subducted, sometimes coming out in a whole different part of the world. Bottom line is there's a massive carbon cycle. It's very complex, but it can have a profound impact on the global climate. So this is how we see the different gases, oxygen and carbon dioxide, dissolving in seawater. Oxygen is abundant near the surface because of the photosynthetic activity of marine plants. So all those plants at the surface, taking advantage of sunlight, are taking in carbon dioxide and spitting out oxygen. So there's very little carbon dioxide close to the surface and a great deal of oxygen close to the surface. Now, oxygen concentration decreases below the sunlit layer because of the respiration of marine animals and bacteria, meaning that animals are breathing out carbon dioxide but taking in oxygen in those lower layers beneath the sunlit layer, let's say 1,000 meters down or 4,000 feet down. And there's no plants at that lower layer. There's no plants to give off more oxygen. So you have oxygen being consumed, but no oxygen being given off by plants. And then oxygen is consumed as well by the decay of tiny dead animals slowly sinking through the area. So in contrast, plants use carbon dioxide during photosynthesis. So surface levels of CO2 are very low. Because photosynthesis cannot take place in the dark, CO2 given off by animals and bacteria tends to build up at depths below the sunlit layer. So CO2 also increases with depth, but because its solubility increases as pressure increases and temperature decreases. So it's a little complex, but you can see that there's way more oxygen at the surface than carbon dioxide. And then carbon dioxide is going to increase as you go down, because biological animals are down in that dark layer. So those biological animals are going to give off CO2 and they're going to take up oxygen. All right, let's talk a little bit about ocean surface conditions. Average surface temperature and salinity for the world ocean. As you would expect, temperatures are lowest at the polar regions and highest near the equator. Heavy rainfall in the equatorial region refreshes the ocean near the equator, where the hot and dry conditions in the subtropics results in higher surface salinity. Meaning at the equator, you have a lot of fresh water falling out of the sky, so you have lower salinity. But at about 30 degrees north and south latitude, those are where the world's deserts are, because of the global atmospheric circulation. You have a lot of sinking air there, you don't have much rain, and so you have high salinity in those areas. So the salinity changes at the surface based on essentially the atmospheric conditions and the climate. Sea surface temperatures during the northern hemisphere summer, pretty straightforward, exactly what you'd expect. They're going to be warmer at the equator and then colder up at the poles. Variations in temperature, salinity, and density are usually confined to the uppermost 2,000 meters. The deep ocean is nearly as salty, cold, and dense as the equator than as it is at the poles. So Yeah, that difference in salinity and temperature, that occurs at the surface. Once you get deep down, there's not a lot of changes in salinity and temperature. And there are your sea surface average salinities in parts per thousand. Those highest salinities at about 30 degrees north and south latitude, and the lowest ones there very close to the equator. All right, let's talk a little bit about acid and base solutions. An acid is a substance that releases a hydrogen ion in solution, and a base is a substance that combines with a hydrogen ion in solution. And so you get alkaline solutions, a solution that is basic, and then you have acidic solutions. And so acid or alkalinity is measured on the pH scale. And you've probably heard about the pH scale most of your life, a couple different views of the pH scale. So an acid is a substance that releases a hydrogen ion, an H plus in solution. Excess H hydrogen ions makes it acidic. A base is a substance that combines with a hydrogen ion. So a solution containing a base is called alkaline. They typically have an excess of OH plus. So acidity or alkalinity is measured on the pH scale, with neutral pH, bases above 7 and acids below 7. So the higher you get above 7, the more basic you are, like drain cleaner, and ammonia, some dangerous stuff, soap. And the further you get below 7, the more acidic you get, such as like tomatoes and then lemons, and then eventually you get hydrochloric acid, a very acidic solution. And so the bottom line to all of this is the pure water is right at 7. Pure water is at 7, but salt water is more acidic, just like milk. You don't think of milk as being acidic, but it is slightly acidic, and rainwater is slightly acidic as well. The more carbon dioxide in the water, the more acidic that water is going to be. So excess carbon dioxide in the ocean acidifies the ocean.
So the oceans had time to adjust to any increase in acidity.
The problem is that today we're pumping out so much carbon dioxide that the ocean just can't keep up.
As a result, they're turning acidic faster than they have for millions of years. The first creatures that will suffer will be the coral that make up the world's great reefs. Their skeletons can't form if the water becomes too acidic. If the oceans continue to acidify at their current rate, coral could eventually disappear from our oceans. With the coral would go all the other life that depends on them.
For ocean acidification, we have a far greater impact than the death of coral reefs. Change in the ocean's chemistry threatens the overall balance of Earth's life support systems. The health of our planet is so intimately connected with the conditions in the sea that these changes may have untold consequences for our world.
If ocean acidification continues, coral would be just the beginning. Phytoplankton are also vulnerable to increasing acidity in the sea. In the long term, this could endanger one of the main sources of oxygen on the planet. But what about the short term? What will these changes in the oceans mean for us? The thing is, the oceans have been stable for millions of years. We are heading into uncharted territory. So we really don't know what the full implications are likely to be. What we do know is that the oceans are fundamental to all life on Earth. Ultimately, the survival of every creature on the planet depends on the oceans remaining healthy.
The difference in temperatures, the difference in salinity with depth causes the ocean to have density differences. There's a complex relationship between temperature, salinity, and the density of seawater. The density of water is mainly a function of the differences in temperature and salinity. And you can see by this chart with temperature on the left and salinity, the temperature is going to be the y-axis, salinity the x-axis across the horizontal. And the lines of blue, those represent density levels, 1.024, 1.025 grams per centimeter. You can have the same density with different or varying amounts of temperature or salinity, but as the ocean becomes density stratified with the least dense on top and the densest water below, you get this very specifically layered setup to the ocean structure. It causes the ocean to be divided into three density zones: the surface zone, the syncline, and the deep zone. The surface zone is the uppermost layer, or the mixed layer, that has the least dense water. It's the warmest and it's the least saline. And up and down mixing, vertical mixing through the waves and currents keeps the temperature and the salinity pretty constant in that first 150 meters, making up about 2% of the ocean volume. And then the next zone down, more dense, is the zone in which density increases with depth, containing about 18% of the water. This extends from about 150 meters to about 1,000 meters. And this layer separates the surface water from the densest water below. And this layer represents a rapid density increase. The water is becoming colder and saltier, and the density is increasing. Now, the deep zone contains about 80% of all ocean water. This very little change in density throughout this layer. And the general cause of the increase in density certainly is slight salinity differences, but it's mainly through the deep layer, the difference in those temperatures, with the warmest temperatures at the top of the ocean and the surface zone having the least dense water, and those coldest temperatures in the deep zone having the most dense water. All right, so in most of the ocean, a surface zone and a mixed layer of relatively warm, low-density water overlies the cyclocline, and the density rapidly increases with depth in the cyclocline. Below that lies a deep zone of cold, dense water. The rapid density increase in the cyclocline is mainly due to a decrease in temperature with depth. So in that area, that rapid decrease is because of a decrease in temperature. Now, in some regions in shallow waters near rivers, say, that cyclocline may develop in which the density increases with depth is due to vertical variations in salinity. So we talked about it being due to temperature mainly, but if you have a lot of fresh water, then it could be that you have the freshest water at the top and more salty water below it, and that's what creates the cyclocline. And in that situation, you have a halocline, which is a change in salt. Also, when precipitation exceeds evaporation, meaning there's lots and lots of rain but not much evaporation in cooler climates, you're also going to get fresher water at the surface. And in that case, you're going to have the halocline. So typically that middle zone, that cyclocline, that rapid increase in density with depth is a function of a temperature drop, the thermocline, the drop from warm waters at the surface to colder waters below. But sometimes there is a drop in or a change, an increase in salinity, and that's the halocline. So the cyclocline is a combination of thermocline and halocline, just different regions have different physical setups. So here's a typical temperature profile at the polar, tropical, and middle latitudes. So the polar is in blue with very little temperature difference from the surface to the deep layer. The tropical, where we have a significant temperature decrease from the surface waters down to the deep zone, and then the temperate areas, the middle latitudes, where you don't have as much of a pronounced change. So there is no thermocline in the polar waters. It's all a halocline. It's all a salinity difference that keeps that water in the polar regions density stratified. So water masses have characteristic temperatures, salinities, and densities. Layering of the water masses by density traps dense water masses at great depths. The cyclocline effectively cuts off 80% of the world's ocean from the 20% involved in surface circulation. So density stratification usually prevents vertical water movement. Large volumes of vertical water movement only occur where there is little density difference between the surface and the water in the deep water at the ocean's depths. So here's another view of that, showing the difference between the polar, which is going to be at either end of this chart, to the temperate regions and mid-latitudes, and then the equatorial regions, where you can see the very warm water creates that pronounced temperature difference with depth. next we're going to move to talk about how light and sound moves through the ocean water. It's very interesting, the effects here. Light is a form of electromagnetic radiation or radiant energy. It travels as a wave. Light travels as a wave through space and through air and through water. Sunlight does not travel well in the ocean. Scattering occurs when light is bounced between air and water molecules, dust, and other objects. So as the sunlight travels through the atmosphere, about half of it is either scattered or reflected away before it strikes the surface. And then absorption occurs when the light's electromagnetic energy is converted into heat in seawater molecules. So when that light strikes the surface of the ocean and heats it up, then there's some absorption of that electromagnetic radiation. So there's a thin film of lighted water at the top of the surface zone, and that's called the photic zone. Because of the scattering of light by water molecules and air molecules, and because of the absorption of electromagnetic radiation of light by water molecules, there's only a thin film of lighted water at the top of the surface zone, and that thin film is called the photic zone. So sound and light both travel in waves, and because they travel in waves, there can be refraction or reflection or scattering or absorption, as I said. Refraction is the bending of waves. So light waves and sound waves can both be bent. And that occurs when waves travel from one medium to another, specifically mediums of different densities. So here you have the white light of sunlight traveling through the less dense air, and then you can see it strikes where there's some sea spray. There's a lot of water vapor in the air, and it literally bends those light rays because it's a more dense medium, and so it literally bends the light rays. So the refractive index is a ratio that expresses how much light is refracted from one medium to the other, and the refractive index of water increases with increasing salinity. So as the salinity goes up, becomes more dense, the refractivity of water increases as well. So that's its ability to bend light waves or sound waves. So water transmits blue light more efficiently than red light. So if you take all of the sunlight, we refer to that as white light, all of the visible light from the sun, it's between about 300 and 800 micrometers of wavelength. That's literally the length of the waves between one crust and the other. And so the blue light travels through water most easily. So only a thin layer of surface seawater is illuminated by the sun. Except for light generated by other living organisms, most of the ocean lies in complete blackness. Now, absorption of light by different wavelengths by seawater can be seen here, where much of the reds are absorbed, a lot of the oranges and the violets, but a lot of the blue is allowed to transmit into the ocean, and that, of course, is the reason why the ocean does look blue. Now, sound travels in the ocean, and there's a real relationship between the water depth and the velocity that the sound moves. So sound's velocity in the atmosphere is somewhere between 1475 and 1500 meters per second. Once it goes into the ocean, as it gets deeper and deeper, there is a higher sound velocity initially, and then the sound velocity drops to a minimum, and then again at great depth, that sound velocity will begin to increase. So sound can travel for much greater distances in water than in light. So the reason why sound can travel greater in distances is because the water molecules are touching each other, and so the compression nature of those sound waves moves the water more easily. Of course, if you put your ear down to the desk and knock on your desk, you'll know that sound moves most easily through solids. So the speed of sound in seawater increases as temperature and pressure increases. So the speed of sound increases with increased pressure, but it also increases with increases in temperature. So there's an interesting thing where you see a drop in temperature and then a drop in speed with depth, and then as you get much, much deeper, the increase in pressure causes the velocity of the sound to increase again. So you have a very interesting curve there relating the speed of sound through water with the depth of the ocean. Refraction bends light and sound, and it also bends waves or ocean waves. So this is an analogy for refraction. We talk about density differences. If you have pavement and sand, and you have a marching band marching along, and we're going to consider the pavement pavement to be less dense and the sand to be denser. I mean, walking through sand is more difficult than walking across pavement. So the ranks of marchers represent the light or sound waves. The pavement and the sand represents different media. The marchers can walk faster if they stay on the pavement, and then if they walk through the sand next to the highway, the sand is denser. So if the marchers head off the pavement at an angle other than 90 degrees, their path will bend, refract as they hit the sand, because the people walking into the sand initially will slow down, and that will cause them to slow down and cause in order for the line to catch up and be straight again, the people on the outside have to speed up, and that causes that wave to bend. If they march straight off the pavement, the ranks will just slow down, but they won't bend. So this difference in density is what bends or refracts sound waves or light waves. So there's a thing called the SOFAR layer, which is the sound fixing and ranging layer, in which sound waves travel at their slowest speed. Sound transmission is particularly efficient, that is, it can be heard for great distances because the refraction tends to keep the sound waves within that layer. So at that layer of minimum speed, the difference in the density to above and below causes the sound waves to bend back into that layer, that SOFAR layer, that sound fixing and ranging layer. And so the density difference below the density difference above causes the sound waves to bend into that one channel, which means that sound transmission is very efficient at that level. And when we talk about listening within the ocean, if we put listening stations down at that level, that 1,000 meter level, that 3,000 plus feet level, you can hear literally in the ocean from all around the world because sound travels so efficiently in that SOFAR layer. All right, and so looking at the last slide here for the lecture 6, this is basically looking at sonars and how sonars work. Sonars just emit a sound wave, and then the sound wave goes down and reflects off of an object, and the sonar listens for the reflection to come back. So the principle of active sonar, pulses of high frequency sound are radiated from the sonar array of the sending vessel. Some of the energy of this ping, this emission of high frequency sound, reflects from the submarine and returns to the sending vessel, and the echo is analyzed to plot the position of the submarine. Pretty standard stuff, and we talked about that earlier in the semester when we were talking about how we determine the depth of the ocean.
That wraps up Water and Ocean Structure from the textbook Essentials of Oceanography, the 8th edition, written by Tom Garrison and Robert Ellis from Cengage Learning. Of course, we talked about ocean water, the structure of water, the composition of water, the unique properties of water, and the composition of the ocean itself. Now we're going to begin to talk about ocean and atmosphere interactions. And we'll start that with a lecture on atmospheric circulations.